This video presentation is for 2021 IEEE International Conference on Automatic Control and Intelligent Systems.
Hello, today I will share and present my research project that I have been working on these past few months. But before that, I would like to introduce myself first. My name is Muhammad Afiq bin Muhammad Alimi and I'm 24 years old. I recently graduated in Electrical and Electronic Engineering Communication from UPenn in 2020 and currently pursuing my master's degree in the same field. My research interest is in control theory and system. At the moment, I am working on developing control strategies and collision avoidance system to improve tracked vehicle maneuvering capabilities.
Maneuver Control and Obstacle Avoidance System for Tracked Vehicle Robot. Introduction.
Many advanced in technology nowadays have been the byproduct of the use and exploration in chemical substances that can be very dangerous and poisonous to humans. Often most, this chemical substance can also have an adverse effect and quite harmful if it was not properly treated, such as a nuclear waste. In such case, semi-autonomous vehicle robot should be the first responder in this particular case instead of human involvement. This is because the robot capable to perceive, grasp, cut, and manipulate depending on the type of chemical waste. Other than that, the tracked vehicle robot capable of adapting to a variety of complex surface and environment. Once the waste was discovered, the substance can then be stored safely or disposed appropriately. On March 11, 2011, Eastern Japan experienced one of the worst earthquake and tsunami that causing heavy casualties and losses. In addition, the Daiichi nuclear power station was also damaged and resulting in releasing of radioactive material. In such event, the use of remotely operated robot may be a good alternative as it can reduce the risk towards the human operators.
Problem statement.
The technology to deploy remotely operated vehicle to replace human operator are readily available, but it must be equipped with enough capability to ensure good information can be extracted so accurate decision and planning can be executed successfully. One of the capabilities is to able to maneuver on an unknown terrain, possibly harmful and compromised area. Thus, the robot must be flexible in terms of its movement, which it can maneuver in various types of surface such as muddy, grassy or sandy terrain without compromising the outcome of the operation. In order to achieve that, the robot must be equipped with a proper control system by using a suitable controller. This is because one of the crucial structure design of this robot is the control system for the maneuvering of the robot. In addition, this semi-autonomous robot must have the capability to steer away from the obstacles. In other words, this mobile operator must be also equipped with an obstacle avoidance system. Finally, uneven surfaces will influence the level of stability of the robot and will affect the performance of the motors. Therefore, this semi-autonomous robot must be equipped with a stability control system which will enhance the capability of the robot to move and maneuver through various types of terrain.
Objectives.
There are three objectives for this research project. First, to study and design the suitable control system for the whole tracked vehicle robot in terms of movement. Second, to create and design the subsystem, which are the stability system and the obstacle avoidance system. Finally, the third objective for this research project is to integrate all the subsystems with the main control system and evaluate the performance of the robot.
Methodology.
In this research, a downscale fully functional tracked vehicle robot was developed and designed which consists of similar part of an actual 200 kg tracked vehicle robot. All the electrical components such as sensors, microcontroller, and transceiver that were used on this tracked vehicle robot were chosen attentively and able to be implemented on the actual scale in the future. The mechanical parts, on the other hand, are simplified version of a tracked vehicle that consists of the shaft toy-grade materials where the chassis or the body frame are built from an aluminium building blocks and the track assembly made from rubber. The tracked vehicle is controlled by using DC motors connected to each side. The simple input-output relationship of the implementation is represented by the figure on the bottom left side of the slide, where Arduino Mega was used as a microcontroller for this track vehicle robot. It is integrated with the two DC motors mounted for the left and right side respectively. Two infrared sensors were used on the robot to act as the collision avoidance system, while the gyroscope MPU6050 was used to provide real-time states of the vehicle's orientation to represent the stability system. The system for this tracked vehicle robot was designed to be a closed-loop control system which automatically regulates all the process for the collision avoidance and the stability control. Plus, the whole system for this tracked vehicle robot can be divided into three subsystems, which are collision avoidance, yaw adjustment, and roll detection system.
Program flowchart.
The program for the whole system on the robot can be divided into three flowcharts, and each flowchart process represents the three subsystems. In each process, there will be a requirement or a condition that needs to be fulfilled. If not, it will move on to the next process. The number in each subsystem symbolizes the continuity of the whole system. The first one is the collision avoidance subsystem flowchart. If the IR sensor detected an obstacle that located less than 40 cm from the robot, the process proceeds to a subfunction. In the subfunction, the input from the IR sensors will go through a PID process that will come out with an output, which is the speed of the DC motors. This output overrides the RC controller input. Then the tracked vehicle will reverse for 1 second and continue to the next process. The second one is the yaw adjustment subsystem flowchart. The input for this system is the yaw reading of the gyroscope of MPU6050 sensor. If the readings show positive or negative values, this indicates the tracked vehicle robot is diverging from its path and moving towards the right or to the left sides. So whenever the yaw readings are past the limit that have been set, the process will proceed to a subfunction which it will undergo a PID process as an input. The output of this process is the speed of the right or the left side of the DC motors will decrease depending on the yaw readings. The third and the last flowchart in this process is the roll detection subsystem flowchart. In this process, the roll readings from the gyroscope is the input alongside with the RC controller. There are two conditions in this case. The first one is when the tracked vehicle robot in the warning level state, and the second one is where the robot in the dangerous level. The positive and the negative values of the readings indicate that the robot is on an inclined surface on the right or the left sides of the tracked vehicle robot.
Results.
In the collision avoidance experiment, there were 4 elements involved and were recorded and presented in the graph. Both IR sensor, throttle, and PWM of the DC motors readings were the 4 elements in this experiment. Result 1 and result 2 is a combination of 2 graphs, IR sensors readings and PWM reading. The T1, T2, and T3 indicates the points where the 4 elements in this experiment changes its behavior. Each element that present in this test were interrelated with each other. Based on both graphs, it showed that the value of the throttle and PWM of the DC motors were almost the same. The throttle values can be considered as directly proportional to the PWM values started from the T1. When the values of throttle input increase, the values of the PWM of the DC motors increase too. However, this process can only be operated if the values of both IR sensors more than 40 cm. The IR sensors act as the main input whenever the threshold, which had been set to the less than 40 cm, it will overrule the input from the RC controller throttle. For example, based on the graph, started from the T3, as the IR1 value decrease, the PWM values also decrease. At this moment, IR1 value can be considered as directly proportional to the PWM values. The result tree shows the yaw adjustment graph, which was a combination of two graphs, the yaw readings graph from the gyroscope of MPU6050 and the PWM readings of the two DC motors, left and right side. These four readings were interconnected with each other. However, in this test, there were two cases that needed to be considered. Therefore, at T1, T2, T3, and T4 were the points where the readings changed its response towards each other. In this experiment, the two cases were the two different input signals from the RC controller, which are forward and reverse input signal. The behavior changes at T1 and T2 occur when the tracked vehicle robot receives forward input signal from the RC controller. Meanwhile, at T3 and T4 take place when the robot receives reverse input signal. At T1, the graph indicates the robot was yawning to the left side, and at the same time, the PWM of the right DC motor was decreased. The higher the value of the yaw readings, the lower the value of the PWM of DC motors. In addition, the graph shows the same behavior at every point. Whenever the robot in forward movement, the yaw R and yaw L were inverse proportional to PWML and PWMR respectively. Meanwhile, when the robot in reverse movement, the yaw R and yaw L were inverse proportional to the PWMR and PWML respectively. Finally, result 4 is the graph for the roll detection subsystem test. As shown in the graph, the roll and the throttle readings act as an input that affected the behavior of the output elements in this experiment. The output elements, LED, and the PWM of DC motors changes its behavior after the point T1 and T2 respectively. The two horizontal dotted lines shown in the graph were the threshold for the roll readings, which these two thresholds represent two different situations. The first situation was called the warning zone, where when the roll value higher than 45 degrees. Then the second situation when the value of the roll from the gyroscope higher than 60 degrees and declared as a dangerous zone. Based on the graph in result 4, the warning LED was blinking when the readings of the roll pass over 45 degrees. Meanwhile, the LED will continue light up when the robot crosses the dangerous zone limit. Plus, the PWM of the DC motors will decrease and stop automatically, although the robot was still receiving the input signal from the RC controller.
Discussion.
Based on all the experiments that have been carried out in this research project, for the collision avoidance and the yaw adjustment system, the result shows that it takes less than 1 second for the infrared sensor and the gyroscope of the MPU6050 to interrupt and replace the initial input value for each system, which is the throttle value from the RC controller. This low response time was an indicator that this system had a good performance time, where the desired output from the sensor reached at the desired value within the time expected. Meanwhile, for the roll detection system, although the output of this system achieved the expected value and response, however, a sudden stop from high-speed maneuver will induce a jerk, which is not good for the traveling vehicles. This rule applies on any vehicle that exists in this world. Therefore, this system needs an improvement that can prevent the tracked vehicle robot from damaging itself. For example, jerk reduction. This will make the robot to slow down gradually and eventually stop within the desired time. In conclusion, this paper presented a design-based research for the maneuvering control and obstacle avoidance system of a tracked vehicle robot. The maneuvering system consists of two separate subsystems that enable the operator to maneuver the robot efficiently. However, some improvement can further explore in order to improve its accuracy and precision during operation, especially in terms of the dynamics of the sensors. Basically, all these subsystems can be used as a precautionary measure for any vehicle-based robot. With the proposed features in the small-scale tracked vehicle robot, it facilitates the operator to maneuver and operate the robot safely and effectively. The next phase of this work is by using the proposed control system along with its subsystems presented in this work to a real-scale remotely operated 200 kg tracked vehicle that allows for more payload to be implemented. It is expected that during this stage, only minimal adjustment is required in order for it to perform during actual operation. With that being said, I have now come to the end of my presentation. I hope this presentation of my research project can be very helpful towards others. Well, that's all I have for today. Stay safe and stay healthy, everyone.
Thank you.